What's up, SUPA peeps? We are going to start the second semester today, and we're going to kind of skip around a little bit. So we're going to start with the nuclear unit, which is chapter 21. So nuclear. So this is when we have unstable nuclides. Also called radioisotopes. Decompose in a process called radioactivity. Radioactivity. So basically, if we have this unstable nucleus, we say that it is radioactive, which means it's going to give off a type of radiation. And this is what we're going to be talking about today. So let's talk about radioactive decay, and then we'll go through some of the different types of it. So this pen is dying. Need to get some new pens. All right, so number one. So radioactive decay is defined as the decomposition of a radioactive nucleus. So when the nucleus goes through radioactive decay, it gives off a large amount of energy. So our nuclei release a large amount of energy. Okay, and this energy is much more than if we're breaking bonds. Okay, so if we break bonds, yes, energy is released. Actually, energy is absorbed when we're breaking bonds. And when a bond forms, energy is released. But this is a much larger amount of energy that we're dealing with. Now, where does this energy come from? So the nuclei releases the energy, and that energy comes from a small amount of mass is converted to energy. And we're going to talk quite a bit about this energy, right? But it's based on a famous equation, E equals mc squared. Right? So this is the relationship between mass and energy. C is the speed of light. Right? So when you convert a very small amount of mass to energy, you actually get a huge amount of energy. Right? So we'll talk lots about that. So any reaction leading to the change in the composition of the nucleus is called a nuclear reaction. So everything we've been talking about up to this point has been a chemical reaction. And in chemical reactions, we're changing or switching the valence electrons. In nuclear reactions, we're changing the protons into neutrons. Let's see if green and red work. Number 4. So when a nuclide decays, okay, in other words, when it goes through, when it decomposes by a nuclear reaction, it forms a different nuclide with lower energy. So remember, in nature likes low amounts of potential energy, right? So when something goes through radioactive decay, it forms a different element. It forms a different nucleus, and that element or that nucleus will have lower amounts of energy, because in nature we tend to go from a high potential energy to low potential energy. Our excess energy is released in the form of radiation. And there are different types of radiation that we're going to talk about. Number 6. So our reactant nuclide the thing that we start with is called the parent material. Our product nuclide or what it turns into is called the daughter material. Number 7. In nuclear reactions, the number of protons, we also often denote that with the letter Z, and the sum of the mass numbers, which is often A, must be equal in the reactants and products. So the number of protons has to remain the same and the total mass has to remain the same. All right, so this is our law of conservation. This is our law of conservation. All right, number 8. So our nucleides decompose or decay in many ways. Right? This is these are called decay modes. Okay, so they're called decay modes. The way it decays, or the specific type of radiation that it gives off, defines its decay mode. And what I want to do is I want to show you the different types of radiation. We're going to make a chart. One, two, three, four, five, six, seven. 1, 2, 3, 4, 5, 6, 7. Wow, that worked out pretty good. All right, so let's put name here. Let's put symbol. Let's put mass, and we'll put charge. All right, so let's run through these different types of radiation. All right, let's start with beta particles. BETA. So beta radiation is, its symbol is a 0, -1 with the Greek letter beta, and it's kind of like a bee with a tail. Right? We generally don't use that very often. Okay, but really what this is, it's an electron. 0 -1 e. So a beta particle is an electron. We all know the mass of an electron. It's basically 0. Okay? Yes, it has an extremely small amount of mass, but in general, we say that the mass of an electron is 0. And the charge of an electron is -1. Okay, so a beta particle has a -1 charge. All right, let's talk about positrons. A positron is actually the antimatter of a beta particle. It's an electron. It's a type of electron, but it's an electron with a positive charge. And the symbol that we're going to use is 0 +1 with that weird B. Well, it's an electron, so its mass is still 0, but its charge is +1. And this is just another type of radiation that's given off. Third type of radiation we're going to talk about is alpha radiation. And this is a helium nucleus. Okay, so we'll use that. Okay. It's also 4-2 with the alpha symbol. It's kind of like a sideways fish. But generally, we're going to use this 4-2He. So our alpha particle, or alpha radiation, okay, is the release of a helium nucleus. There are no electrons around it. Its mass is 4 AMU, right? And here it is. And the charge of the helium nucleus is +2. It's lost helium's 2 nucleus, or 2 electrons. All right, so it's got a +2 charge. We can produce protons, right? And its symbol would be 11H. Sometimes you'll see 11P. okay, for a proton. But remember, a proton is really just a helium nucleus. It's got a mass of 1 AMU, and it's got a +1 charge, because this helium nucleus has no electrons. We can produce neutrons. One 0N has a mass of 1 AMU, and a neutron has no charge. And then finally, the last one is gamma rays. And gamma rays are not particles, they're energy. And its symbol is 0, and this is the letter gamma, the Greek letter gamma. It's kind of a weird Y, something like that. It's curvy. And since it's energy, it has no mass, and it has no charge. Now, you need to learn this. Memorize. Okay, you need to know what the symbol for a beta particle is. Its mass and its charge. Same thing for a positron, same thing for an alpha particle, protons, neutrons, and our gamma rays. You're going to need to know these. Okay. Now, what we're going to do is we're going to go through some of these radioactive decay modes. Okay, and we're going to learn how to write these equations. So let's talk about alpha decay. So when we're talking about alpha decay, that means we're producing an alpha particle. Or we're producing a helium nucleus. Okay, that's the radiation. Alpha decay or alpha particles are very heavy. In comparison to the other ones, it's got a mass of 4 AMUs. Right? So it's very heavy. So because it's so big, because it's so heavy, it will travel only a few centimeters before losing its kinetic energy and gaining electrons to form ordinary helium. So it doesn't move very far. So because it doesn't move very far, because it's so heavy, its relative penetrating power is equal to 1. Right? And I will give you these numbers as we go through. Okay, so it doesn't penetrate very far. So if you have to get irradiated by some type of radiation, right? Not that any type is good to get irradiated by, but this is one that is going to hurt you the least, right? Because it has a relatively low penetrating power. Now, an example of this decay mode, radon 222 goes through alpha decay. Right? So we can write this nuclear equation. Right? So what we do is we start with radon Rn. Its mass is 222. Okay, it has 86 protons. Okay, so this is what's called the parent material. This is the parent, or what we're starting with, a radioactive nuclide. And it's going to go through radioactive decay. It's going to go through alpha decay. We put an arrow. And as soon as I know that it goes through alpha decay, I'm going to write the symbol for an alpha particle, 4,2He. So this is the radiation it's going to give off. So how do I come up with the daughter material, what it comes into, what it turns into? Well, we're just going to subtract. 222 minus 4 is 218. 86 minus 2 is 84. If I look up 84 on the periodic table, it's polonium. And this is my nuclear reactant, and it's balanced. And it's balanced because the mass on this side is equal to the mass on this side, so we add those two together. And the number of protons on this side is equal to the number of protons on this side. So it's balanced. Now, this is the parent material. Okay, and this is radioactive. The polonium is my daughter material. Okay. It's what the radon turns into. And this guy right here would be my radiation. Okay, so this alpha particle is my radiation. This, the polonium's daughter material, is going to have less energy than the radon. So this guy's unstable, and it's going to give off the radiation to become polonium. All right, that's our first type of decay. The second type of decay we're going to talk about is beta decay. So this is when a neutron in the nucleus is converted to a proton and a beta particle. All right, now, we're talking about this. Remember, the beta particle is just an electron. So this is an electron that's being produced in our nucleus. Now, I don't want to go into a lot of physics, but you got to remember that protons and neutrons are made up of quarks. And those quarks come together in different ways to form protons, okay, and neutrons. Okay? And we can convert between protons and neutrons, and we are giving off these particles when we do that. Right? So in beta decay, we're starting with a neutron, and it's producing a beta particle. Okay, so there's my beta particle. So if we subtract, what's 1 minus 0? 1. 0 minus the negative 1 is 1. It's positive 1. When you subtract, you add. And this would be a proton. So this is the conversion of a neutron to a proton in the nucleus, and this is my beta particle. So these guys, in comparison to our alpha particles, are very small. And these will travel about 300 centimeters in air. Quite a bit more than our alpha particles. So they can penetrate our skin. But not normally. They're usually absorbed in the skin. They won't get past our skin. Right, so this gives it a penetrating power about 100. So it's 100 times more penetrating than our alpha particle. Okay, just give you a relative penetrating power. An example of this decay mode is carbon-14. Carbon-14, which is what we use for radioactive dating of organic material, old living material, goes through beta decay. It's going to give off a beta particle. So we can actually write this equation. So carbon-14, which is the parent material, it's going to go through radioactive decay, and it's going to give off a type of radiation. Okay, so as soon as we know what type of radiation it produces, and we know it's beta, we're going to write the beta particles. 0 minus 1e. And then we can figure out what the daughter material is by subtracting. 14 minus 0 is 14. 6 minus a negative 1, which means we're 6 plus 1, is 7. And this would be nitrogen. So again, this is my radioisotope. All right, this is my parent material. This right here is my radiation that's given off. And then this is my daughter material. Now, the ultimate goal of a radioactive substance is to become stable. And we're going to talk more about that next class. All right, but that's why this is going through radioactive decay. It wants to become stable. Well, it's going to give off energy to try to get there. Good. So let's talk about our third type, and this is what's called neutron decay. Which means it's going to give off a neutron. This is very penetrating. And it will easily pass through material because there is no charge. Right. Because it can go through here, it can cause significant damage. And because it doesn't have this charge, it easily will, okay, it'll easily pass into our body, right? And if it gets absorbed by, I don't know, say our DNA, it can cause a mutation. Not many substances go through neutron decay. One of them that does is krypton-87. Okay, so krypton-87, this is our radioactive substance. It's our parent material. It will go through neutron decay. So as soon as I know that it goes through neutron decay, we write the symbol for a neutron. So that's our radiation. That's what it's going to produce. And then we can figure out the daughter material by subtracting. 87 minus 1 is 86. 36 minus 0 is 36. right? So it's still a type of krypton. It's still a type of krypton because it has the same number of protons, right? But it has a different number of neutrons, right? So these would be isotopes to each other. They would be isotopes. This has less energy associated with this one, though. This one's pretty unstable. And it gives off this neutron, so this is my radiation again. Okay. This would be my daughter material. And this is my parent. All right, so let's go through our next type, and this is called positron emissions. Oops. So remember, this is it's the positive equivalent to an electron or beta particle. Okay, so this is an electron, but it just has a positive charge. Okay. So it's an electron with a positive charge. Now, how is this positron produced? Well, again, this is changing the nucleus. So this is kind of the opposite. This is the opposite of beta decay. This time we're going to start with a proton, and it's converted to a neutron. So we're taking a proton and we're converting it to a neutron. So if we start with that symbol for a proton, it goes through beta decay, but it's going to produce a neutron. So we got 1, 0, n. Now if we subtract to balance this out, 1 minus 1 is 0, so it has no mass. 1 minus 0 is plus 1 still. So we have a particle with no mass with a positive charge. Okay. And that would be our positron. That's our positron. Well, just like that beta particle, it's small and very light. And it doesn't penetrate well. They don't penetrate matter well. So their penetrating power is just like a beta particle. So our relative penetrating power is equal to 100. So our positrons are considered to be antimatter. Now, what happens when matter and antimatter touch each other? Well, in this case, okay, we're talking about this positron, and if it encounters an electron, crazy crap happens. Crazy stuff happens. So the positron is annihilated when it encounters an electron. As soon as they touch both the electron and the positron, are converted to pure energy. And it's in the form of multiple gamma rays. It produces multiple gamma rays. Okay, it happens instantaneously. Right? So carbon-11 is an example of a substance that goes through positron emissions. So if I wanted to write the nuclear equation for this, I take my parent radioactive material. I know it goes through positron emissions. So I'm going to write 0 plus 1 with that weird B. That's my positron. Now I can come up with my daughter material by subtracting. 11 minus 0 is 11. 6 minus positive 1 is 5. Okay, so it turns into boron. Again, parent material, it's radioactive. Here's my positron that it produces, right? And here's my boron, my daughter material. So we're taking a proton, okay, and we're converting it to a neutron. So the number of protons changes, but my mass stays the same. All right, we got 2 more types. Let's talk about electron capture. And it's also sometimes called K electron capture. In electron capture, what happens is an electron from the first PEL, okay, from our inner principal energy level, remember, which means n equals 1, falls into or is captured by the nucleus. So an electron from the first principal energy actually falls into the nucleus. This transforms a proton into a neutron. So what does that look like? Well, if we take a proton and we add an electron to it, okay, remember this has to add up to this side, right? So 1 plus 0 is 1. 1 minus 1 is 0, and that would be a neutron. Right? So this is electron capture. Now, again, not a lot of substances will go through electron capture. Rubidium-82 is one of them. So its equation would look something like this. Rb82 has an atomic number of 27. It captures an electron 82 plus 0 is 82. 27 plus negative 1. This should be 37. I'm sorry. 37 plus negative 1 is 36. And that's done. So this is a little bit different than the other ones we were dealing with, because the other ones were giving off radiation. This is different in that it's absorbing this electron from the inner principal energy level, and it's converting it from one element into another. This is still considered my parent. And this is my daughter. All right. Finally, the last one we're going to talk about is gamma ray production. And it's that Greek letter gamma. This happens right along with many of the other radioactive decay modes. All right, so some radioactive decays will produce high energy photons called gamma particles. Okay, so this is electromagnetic radiation. So another example of electromagnetic radiation is light. Okay, so this is, okay, it's got photons that are wave-like, travel in a wave-like motion, right? But gamma rays have much more energy than that light. Okay, so this is an electromagnetic radiation. Have very short wavelengths. And high energies. They have a very high penetrating power. They will go through most objects. They will cause major damage. Our relative penetrating power is equal to 10,000. So to stop these, you're going to need inches of lead. Okay, so like when you go to the dentist or you get an X-ray, they put a lead vest over you, right? Those are to stop X-rays, all right, which are nowhere near as penetrating as this one. So you're going to need inches of lead to stop it. Or you're going to need meters of concrete. Okay, so when we think of a bomb shelter, you're talking about large amounts of concrete to absorb those gamma rays. Okay, that's how powerful they are. So our gamma rays do not have mass or charge. So they do not change the mass or protons of the radioactive nuclide. So what'll happen in those decay modes that we just went through? So for example, radon 222 goes through alpha decay. Oops, not PO, PO. So we already wrote this. So this is an alpha decay, but it will also give off gamma rays. Okay. Now, where do these gamma rays come from? This is where our small amount of mass is converted to energy. Now, what do I mean by a small amount of mass? We're talking about a amount of mass that you can't really even measure, right? But it still produces huge amounts of energy, right? So this would be my gamma rays. Right? All right, so those are the different types of radiation and the decay modes that they go through. All right, so that's where we're going to stop for today. And we will pick up with nuclear stability, all right, next class. All right, have a good one.